Alright, our last class today. So, today we're going to finish up talking about some non-parametric tests. There are lots of other non-parametric tests. If you're interested in them, you can Google them. But today we're going to talk about Friedman and Kruskal-Wallis non-parametric tests. So, the last two classes we've been talking about Wilcoxon tests. The Wilcoxon tests were basically non-parametric alternatives to the t-tests, right? So we had three different types of t-tests, one sample. We had the two independent samples and the two paired samples as well. So we had t-tests for each of those. And if the assumptions about a normal distribution were violated, you could use a Wilcoxon instead. So in class, the thing that we discussed after we talked about the t-tests was ANOVA, right? We talked about a number of different types of ANOVAs. We did One Way ANOVAs, repeated measures ANOVAs, factorial ANOVAs, and we did, the mixed ANOVAs. We are not going to go through non-parametrics for all of those. So we are going to just talk about the One Way ANOVAs. So when we wanted to know whether two groups were different, whether there's a difference between the means of two groups, we use the t-test or the Wilcoxons. Right? So if we want to see if two or more groups are different, we use the ANOVA. And basically what we did is we compared variance, or sums of squares, or the mean squares, right? We had mean squares for an effect, and then also the mean squares that was related to error. So we're going to see something that's very similar to that today. Okay, when we use repeated measures, why did we do this? Yeah, by using a repeated measures design, what we were doing was we were breaking up variance, right? We were saying by knowing which person participated in each condition, we can potentially explain some of the variance and give ourselves a better opportunity to see if there actually is an effect. So we're going to do something similar today too. Okay, this should be, oh good grief, ANOVAs and non-parametric. So we have our independent measures ANOVAs. This would be a one-way, but we're not doing repeated measures. All the measures are independent, right? Just a normal old one-way ANOVA. So for our alternatives for the independent measures ANOVA, we have a Kruskal-Wallis test. For our repeated measures ANOVA, this is where we were looking at the same person in multiple conditions. We're going to use the Friedman test. These, just like the Wilcoxon tests, are all based on ranks. Okay, so let's imagine a hypothetical situation. Imagine that we want to do a study where we manipulate emotion by having participants watch a movie. So we want to see how emotion affects something, right? We're going to have one group of subjects maybe watch a sad movie, and another group of subjects use a control movie, okay? Now that's potentially something that we could use an ANOVA for, but forget about all of that. First we need to figure out what movies that we're going to use, right? So what movie do we show our participants? If we want our movie to have some effect, if we want our participants to be sad as a result of our manipulation, we should use a movie that ends up making people sad. Does that make sense? So what movie do we show our participants? Let's say we take 3 movies that we find really sad. What movies do you guys think are sad? Titanic is sad. Okay, Titanic, I did this IMDb search this morning for like saddest movies, and Titanic was like on the top 10, I believe. What else? I didn't use that.
P.S. I Love You. P.S. I Love You.
P.S. I Love You. I have not seen that. Is that sad?
Yes.
It doesn't sound like a sad movie. Oh, by the way, I love you. No, okay. So let's say we take 3 movies that we find really sad. So she finds P.S. I Love You really sad, but maybe it's actually a happy movie and she's just crazy, right? Possibly. I don't know. I haven't seen it yet. It sounds like a happy, love, romantic movie. Okay. So we've got our 3 movies selected. Now we're going to show them to participants. This isn't in the study where we actually manipulate to see if it has the effect. This is what's called a pilot study. We want to do a pilot study to see if something works, to try to get a sense of what we're going to do in the real study. So we're going to have people watch these movies, and then we're going to have them rate the movie on a scale from -10 to 10. Okay? So how sad or happy was the movie? So a negative 10 would be like, this is the saddest movie I've ever seen. Whereas a positive 10 would be like, it wasn't sad at all. It was like the happiest movie I've ever seen. Okay? So we have them rated on some scale that we just made up. I made this up. I've never seen a scale that works like this. Usually it's 1 to 7 or 1 to 10 or something, not negative. But anyway, whatever. You can make up whatever type of scale you want. So imagine that we're going to have 5 people rate each movie. 5 people watch P.S. I Love You, 5 people watch Titanic, 5 people watch Anchorman. I don't know. Okay, so here are the data. So we have ratings from, of 15 different watchings of the films. And here are the movies. So I picked Old Yeller. Have you guys seen Old Yeller? It's a story about the little boy with the dog. And I won't give it away for those of you who've seen it. Sad movie? Happy movie? I thought it was a sad. Forrest Gump. You guys seen Forrest Gump?
Yeah.
I did not think that this was a sad movie. It has sad parts, but overall, I didn't really think it was a sad movie. So I was surprised when it showed up on the saddest movies of all time. And then, for the third movie, I picked One Way ANOVAS. Have you guys seen that? Oh, yeah, I've seen it. Oh man, if you haven't seen it, they have it in the library. It's really sad. In my opinion, we could have people like rate the movies. Okay, so we have 3 different movies, and we have the ratings for the 3 different movies, okay? So let's see how we could do this in R. You might say, well, let's just do a regular old One Way ANOVAS, okay? But let's assume that these are not normally distributed. We really don't have that many observations per movie, only 5 observations per movie. So maybe this isn't a very good assumption. So let's not use ANOVA, and instead we'll use a non-parametric test. Kruskal.test, or the Kruskal-Wallis. Similar to binom.test, or chord.test, or t.test, Kruskal.test. Ratings, squiggly movie. Okay, what does that mean? Ratings, squiggly movie. We want to analyze our ratings as a function of movie, or as modeled by the different movies that we have, right? So this is basically just like a formula that we created for our analysis of variance, or like the formula that we later created for a correlation test, or like the formulas that we saw last class we can actually use for our Wilcoxon test as well. Okay, so let's do that. Kruskal.test ratings is a function of movie. Here it is. So we see ratings by movie, Kruskal-Wallis chi-squared equals 4.82, degrees of freedom 2, p-value is 0.08. What do we do? Fail to reject. That's exactly right. Why? P-value is greater than 0.05, right? Okay, so we have no statistically significant difference in the ratings of the movies. This means that participants basically find all of the movies equally sad, or equally happy, or equally neutral. What would the null hypothesis be? So with the null hypothesis for the ANOVA, do you guys remember what it was? All of the means are the same. So here we would have the similar type of null hypothesis. All of the medians are the same. All of the means are the same, right? Okay, so apparently there's not enough evidence to reject that null hypothesis, right? So we failed to reject that null hypothesis. How do you think we got this df equals 2? We have 3 movies. That's right. We're interested in differences in the 3 movies. So we have 3 movies. Once we know, 2 of them, we know the final one. So we've got 2 degrees of freedom. Finally, we have this thing called the chi-squared. We know what a chi-squared is, but notice that this is not just chi-squared. This is Kruskal-Wallis chi-squared. It's not actually a chi-squared, but it's something that is similar enough to the chi-squared that we can use the chi-squared to approximate. Okay, So let's see how we do this Kruskal-Wallis chi-square. So the first thing we're going to do is we are going to rank all of the data all together. Right? This is exactly like we've done previously in the independent Wilcoxon, right? We get all of the data, then we rank all of the data together. Okay, so which rating should get a rank of 1? Minus 8.6? Is there anything smaller than minus 8.6? No. Okay, so that should be our first one. What should be our next one? Minus 4, this one? Is there anything smaller? No. And our third? This one? That one. Yeah, so basically the rankings of the ratings is very straightforward. Just rank it just like you would. You have everything together, ranked from smallest to largest. Okay, so we have our ranks. Now the formula for the Kruskal-Wallis chi-square is this. K equals big N minus 1 times some sum of stuff divided by some other sum of stuff. So N here, this is the total number of ranks. How many ranks do we have total?
13.
Not 13.
15.
15. We have 15 ranks, right? We have 15 observations, or just the total number of observations. So this is going to be 15 minus 1. NG, this is the number of ranks we have in each group. So how many ranks do we have for each group?
5.
5 ranks for each group. We have 5 ranks for Oldianer. We have 5 ranks for Gonu. And then 5 ranks for Gun, right? So we have 5 per group. Now, if you guys remember back when we talked about the non-repeated ANOVA, we said that we could have different numbers of observations per group. And that's the same thing here too. It so happens that we have 5 for each group in this design, but we could have had 4 for one and 8 for the other. Okay? So it's not imperative that you have the same number of observations for each group. This time it works out that that's the case. Okay, so what's next? R, as we see down here, R is just a rank. So here we have a rank. This rank is 12. This rank is 14. That rank is 1. This, the R with the thing over it. Remember when we used that flat line over X, that meant the mean of X, right? So here what we're taking is a mean of ranks. So R with the hat over it, this is the mean of all of the ranks. So we're going to add up all of the ranks and divide by the number of ranks, and we'll get the mean rank. Okay, finally, so that's, we have this, we have this, we have this, we have these two. What do you think that one is?
What's
K. K. This is the Kruskal-Wallis chi-square. It's a symbol for it. One of those.
Range.
So this is going to be the test statistic, this K. So if you look back, oh, I guess it didn't say K, but this is K, with 4.82. Yes, we will find the p-value according to this K, the K that we're calculating for 2 degrees of freedom. Right? So we can just use 1 minus p chi-square 4.822.
Why not 1?
Why 1 minus?
Because we used with F2. We used with F like 1 minus P. Is it because it's chi-square?
It's because it's chi-square. Chi-square and F, remember, you are only looking for, they are non-directional tests. You can't have the greater than or equal to. It's just, they're all the same. All of the means are the same. All right. So let's go back and see if we can see how the chi-square was calculated. So we have this formula, and we described what all of these pieces are except for this. So what do you think that piece is?
Each ratings.
It's going to be ratings, or ranks actually. What type of ranks? Has that little thing over the top.
Mean.
It's going to be mean ranks for what? This was the mean of all of our ranks.
It is for particular.
So it will be the mean of the ranks for each group, right? So we'll have a mean rank for the group altogether, a mean rank for our group Gomlu Yarsı, a mean rank for Scum. Okay, so that's just the group mean of ranks. So let's take a closer look this morning, all right? And this might help us to understand why we're using the chi-square, and it might help us to make sense of exactly what this is. So we have this. Does anyone notice anything about this that's similar to what we've seen before?
Unbiased.
N-1. We used an N-1 previously when we were trying to get an unbiased variance estimate. Okay?
And,
What? Square? What about a square? We have sum of squares. Where? We have a sum of squares? Where?
It was effect and error.
We had sum of squares for effect and sum of squares for error. This was when we were doing the ANOVA, and then we divided by the appropriate degrees of freedom to get the mean squares. But where do you see sum of squares here?
Both. Sum of squares for effect and sum of squares for error.
Yeah, but where do you see them?
It's subtract.
The denominator. This is the sum of squares. Oh my goodness, that's right. You're taking something, you're taking a difference, you're taking a deviation, and you're squaring it. That's the sum of squares. And what else? Oh my goodness, yeah, the numerator, that is also a sum of squares. Right? You are taking a sum of something that you've squared. This is a weighted sum of squares, but it's still a sum of squares. Right? So we have two sums of squares. And this is sort of like the sum of squares for our effect. Remember when we were doing ANOVA and we wanted to get the sums of squares for our effect? What we did was we subtracted the mean for the group, we subtracted the grand mean from the group mean, right? So we found out what each group mean was, and then we subtracted the grand mean from it, and then we multiplied it by something. That's exactly what we're doing here. We're taking the grand mean and subtracting it from each group mean, and we're multiplying it by something. So that's very much like the sum of squares that we've seen previously. But what is this denominator like?
Error.
Is it like the sum of squares for error? Do you guys remember what the sum of squares for error was when we were doing our ANOVA?
Each individual with
Yes, each individual minus
subtract from the mean.
from the grand mean.
No, not grand. Group mean.
Yeah, when we were doing ANOVA, the sum of the squares for the error was each score minus the group mean. So this is not like the sum of the squares for the error. Instead, this is like a different type of sum of squares.
We subtract each rank from grand mean.
Each rank from the grand mean,
Total?
that's like the total sum of squares. Yes, that's exactly right. So when we wanted to get the total sum of squares, we just subtracted the grand mean from each of the scores that we had and added that whole thing up, right? So that was the sum of squares for the total. So unlike the ANOVA where we had the sum of squares of the effect divided by the sum of squares for an error, here we have something that's like the sum of squares for the effect divided by the total sum of squares. But what does that tell you? If you divide...
It's giving like error.
It's not giving you the error. You can figure out potentially what the error is, right? So what does this tell you? If we were to find a pen, what does that tell you? The ratio between the sum of the squares of the effect and what the sum of the squares called? It's not a mean square. Let's make this simpler. Imagine that we have 100 sum of squares total. And we have 20 for the sum of squares for the effect. Okay. Yeah?
1 minus this number.
So 1 minus 20.
Not 20. Because effects. The effect is part of the total. How is the
It gives you a percentage,
what part?
right? Basically, this tells us what percent of the sum of squares total that the sum of squares of the effect comprises, right? Imagine a situation where the sum of the squares of the effect equal the sum of squares for total. You'd have 100%, right? That would mean that all of the sum of squares is explained by the effect. Which would be very, very unusual, right? Basically, this is just a percentage. Okay, so we have our sums of squares. We've got our degrees of freedom total. So basically, we're getting a percentage of the sums of squares, and then we're weighting it by the total, by the degrees of freedom for the total, right? Okay, so as the sum of squares of the effect gets comparatively larger, k should get bigger, right? So as k gets bigger, we are more likely to reject the null hypothesis. If we have a small k, we are going to be more likely to fail to reject, right? Just like the chi-square, we want a larger value of chi-square if we're going to reject the null. Okay, so if the means for the groups equal the grand mean, so if there is no difference between the group means, right? All of the group means are the same thing, then the grand mean will be the same thing. So you have, let's say, 27.2 minus 27.2 squared plus 27.2 minus 27.2 squared. We're going to have 0 on top, right? Which will give us a k of 0. So if the mean for all of the groups really is, if the means for all the groups really are the same, then k is going to equal 0. Okay, so let's go through the example. So we have our ratings for the movies. We already figured out what the ranks are for the movies, so now we need to figure out the means. Right? We need to figure out the grand mean. We need to figure out the means for each of these. So what is the mean rank for Old Yeller? You don't have to tell me the answer, but tell me how you would find it.
Sum the ranks?
Sum these things? Sorry.
5. And
So 5 plus 4 plus 11 plus 12 plus 7?
divided by 5.
Divide by 5. So 5 plus 4 plus 11 plus 12 plus 7 divided by 5, 7.8. Right? Let me find the mean of the ranks for Forrest Gump. Do the same thing. 6 plus 8 plus 13 plus 15 plus 14, all divided by 5. We get 11.2. Golnul yarısı, same thing. Now how do we find the total?
We'll all add.
We're going to add all of these together
And divide by 15.
and divide by 15. Or there's something else that you can do too. Yeah, since we have the same size groups for each, we can just add up those 3 and then divide by 3. If you didn't have the same size groups, you'd probably want to add up everything. Okay, so there is our total. Okay. So, we have our ranks. We have our means. If you remember part of the formula, we were taking the grand mean from each of our ranks, right? Subtract the grand mean from each of our ranks. So let's find the difference between each rank and the mean of all of the ranks. So the mean of all of the ranks is 8. So 5 minus 8 is
minus 3,
minus 3,
minus 4,
minus 4, and we've got the rest, right? All we're doing is subtracting this from each of our ranks. Okay. Now, we didn't just want the difference between each rank and the mean ranks. What did we want?
group, yeah.
We also wanted group means, but there was something like the formula. It wasn't just R minus that wasn't it. There was more to it than this.
Sum and square.
We're doing a sum and we were doing a square, right? So we also need to square these deviations or square those differences. Okay, so what's 9? 16, 9, and we've got the rest. Right, so basically we're just getting deviations or differences and squaring them.
Sum.
We're going to need to sum them all up too. Okay, so here's our formula. We have just calculated each individual one of those. Let's sort of move things over and get what we don't need out of the way. So here we have the squares, and we have the means. And with this, we have enough information to solve for that. Okay, so k is equal to n minus 1. What's n minus 1?
14.
So 15 minus 1, that's 14. Okay. Now what else do we need to do? So ng is 5. So this is going to be 5.
It depends on which RG, it depends, either one of those three. RG.
Okay, it depends. We're actually going to sum up over all of these. So for each group mean rank, we are going to subtract the grand mean rank from each of those groups. So what are we going to have?
Minus 0.2.
So minus 0.2, so what you did was 7.8 minus 8. We're going to square that. So this was minus 0.2 squared. And we're going to do the same thing for the next one. So that will be 11.2 minus 8 squared. Plus 5 minus 8 squared. You guys see where we're getting it? So the totals here, here, and here. And then like that, right? So we'll get that part. How about the denominator? Each of the what?
Each observation.
Each observation? So this is the rank for each observation minus the grand mean, which is the deviation, which is squared, but we've already got it, right? So all we need to do is add those up for the denominator. Okay, so let's do it. So for the numerator, we have that. If we go through the math, we'll get 96.4 for the numerator. For the denominator, we have this. We're just adding up all of these individual values. So 9 plus 16 plus 9 plus 16 plus 1 plus 4, etc. We'll get 280. And then all we need to do is multiply the ratio of these two things. So this is like the total sum of squares, and this is like the sum of squares for the effect. So multiply that ratio by 14, and that will give us 4.82. You guys remember what 4.82 was? That was exactly what R told us, was the chi-square. So then if we wanted to manually calculate the p-value, we can do that 1 minus p chi-square. Okay? All right. So it works. Yeah. What if the situation were different? What if we had the same 5 people rate each move? That's a repeated measures, right? So I have her rate all 3 moves. movies. She watches one, she rates the one, she watches the next one, she rates that one, she watches the next one, she rates that one. Then she does the same thing. Then he does the same thing. He does the same thing. So we have every person rate each of the movies, right? So this will control for differences in how people rate. What? Well, what does that mean? It will control for differences in how people rate.
Because you have different people with the error reproduce. So now we have one error for the same person, but the rating is going to be different for each movie.
So one person typically will rate each movie differently. Okay, that's true. And you said something about the error. So there's going to be more error if we have different people rating different movies than if we have the same person rating the same movies. Why? Why would that be?
Because for each movie, we have error for each movie.
So I rate a movie on my scale of -10 to 10. And I rate the movie WALL-E. WALL-E. And I give WALL-E a 6. Right? So WALL-E, to me, is a pretty happy movie, which is actually, it's kind of sad too. But it's pretty happy. I mean, he floats around in outer space with Eva. It's cute. All right, so I give that, what did I say, a 6? I give it a 6. Who would give it something different? And all of you would give it a 6. You're like, oh, Hoja, he knows his movies. I'm going to give it exactly a 6 too.
4.
A 4. Why?
Because it's not so happy for me.
It's not so happy for you. So different people have different ideas about what makes a movie happy. Right? Different people have different days. Maybe she thinks it's a really happy movie, but she's depressed today. So because she's depressed today, she's rating WALL-E lower than it should be. Does that make sense? So this has to do with errors. Some people rate movies very well, like my mom. Oh, I love that movie. Oh, it's such a good movie. Everything is great. Have I told you about my mom? She loves everything. Go out for dinner with her. Oh, I love this food. Oh, I love that picture. Like all of my pictures on Facebook. Like. Some of my pictures are not that good, right? But she likes everything. So she's biased to really, really high ratings. Other people, they're like, this sucks. I hate everything. The sheer trolls, right? Ugh. So what we can do is by having individual people rate each movie, we can sort of take out of the equation their individual biases and all that other stuff that's related to error. So I have you watch all 3 movies on the same day. Your level of depression for that day, I guess if I'm showing you all sad movies, that might be changing over time. So we can counterbalance which movie we show first and second, third, but that's another issue. But anyway, by showing people all of the movies and having each person rate all of the movies, or all of the whatever it is that we're trying to rate, we can control for that error. All right. So, how can we account for these individual differences in rating styles? What did we do when we had a dependent t-test? A paired t-test? We basically just subtracted scores from one, right? Is there anything that we could do for this? Because here we're not really subtracting scores, we're getting ranks. How do we do that? We counted like subjects as a factor. So if we're doing something similar, maybe we can build a model, just like we did in ANOVA, where we said, okay, subjects is part of the error. Maybe we could do something like that here as well. Okay, what we're actually going to do is we're going to end up ranking the data for each judge. So we're not going to get all of the ratings and then rank all of the ratings as one. We're going to get all of the ratings for one judge. And then rank those ratings for that judge. Okay, so imagine she says that Old Yeller. How happy is that? How sad is that? -10 to 10. 6. And the next one was Forrest Gump. Roll yarısı. 10. Is higher, happier or sadder on your scale?
-6, -5,
Okay, okay. So, let's get more possible. Moto? Muto? I don't know. All right, how about you? We'll gather.
2, 8,
Forrest Gump?
-1.
Okay. So if we were going to like do what we did before, this would get a rank of 1. This would get a rank of 2. We have tie ranks here, so 3.5 and 3.5. So it'd be 5, right?
Yeah.
This is 3, 4, 5, and then 6, right? But we're going to do something different here. We're going to rank the data for each judge. So we want the ranks for Melvin, and then again the ranks for Mo. So what are her ranks?
-1.
So we get.
This is -1. Well, ranks are going to go like 1, 2, 3, 4, 5. Right?
The -10 is 1.
This one is 1,
1, 6,
2, 3. How about this person?
-1 is the 1.
1,
2 is
2, 3. So notice before, there's a lot of differences in how they rated the movies, right? Like, he thought Forrest Gump was great. It's a happy, really one of the happiest movies on earth, right? And she thought that it was pretty depressing. So there's obviously some differences in what criteria that they're using. However, when we rank the individuals, we see that she thinks this one is the saddest and this one is the happiest. And we also see that he's agreeing with her, right? He disagrees about how happy it is, but he still thinks that it's the happiest of those 3. Does that make sense? So what we're doing basically is we're controlling for everything else sort of that is contributing to the way that individuals rate the items. Okay, so by ranking the data for each judge, we see which movie each judge thought was the saddest, happiest, etc. If one movie is sadder or happier than others, the judges should tend to rate them in the same order, right? Or close to the same order, even if the ratings that they use are very, very different. Okay, so let's take another look at the data. So we have our ratings, we have our movies, now we need judges. So we have Ayşe, William, Ergun, Felicia, and Elif rating each movie once. Right? So Ayşe watches all the others, she watches Forrest Gump, she watches all the others. So we have our ratings, we have our movies, and we have our judges. What is that? Ratings? I think maybe I am doing a ranking. Yeah. So this should be rank. So what we want to do now is just look at Ayşe and see how Ayşe rated the 3 movies. So which one gets a 1?
-4.
The -4, the bottom one does. Which one gets a 2?
-2.
All the other does. Forrest Gump? Yeah, it's what's left over, 3. Okay, how about William? So let's look at William and let's rank William's ratings. So William also, the bottom one should be 1, the top one should be 2, the middle one should be 3. What happens when you make up data? Sometimes you make up data that is really perfect. So if you look at this, all of the ranks are exactly the same. I promise when I give you homework, I will not make the data this clean for you. I'll make it a bit more messy. But basically here, all of the raters are in complete agreement about which movie is best and which movie is worse, right? Now before, when we did the previous test, when we did the Kruskal-Wallis, we saw what? No difference between the movies. No statistically significant difference. However, when we account for the individual differences, it looks fairly convincing to me that Kruskal-Wallis is the saddest. Alright, so although our judges disagree about the ratings, they basically all agree on the order. Right? Order. Right. Sweet. You'll probably never see agreement this strong in the real world with interesting questions. Non-interesting question would be like, what movie is happier? What's a happy movie? Happy Feet? There you go. Versus Saw. Right? Everyone probably is going to agree on the ratings for that. No, you don't think so? You think some people would rate Saw as very happy? Maybe. All right, so let's take a look at how we analyze the data. So, we did a Kruskal-Wallis test when we had the independent observations. When we have the paired observations, or the dependent observations, we're going to use a Friedman test. Friedman, not test. What do we have? Ratings, squiggle movie, bar judge. What is that?
Just read it like that.
It's not nesting.
Similar to.
It's a bit different than.
Ratings, movie, judge, and according to.
So we're going to create ratings as a function of movie, controlling for judge. Now, if you guys remember way back to the beginning of the semester, we talked about PA, this B, and that meant the conditional probability. What is the probability of A if we know B? We can say this differently. What's the probability of A if we hold B constant, if we control for B, right? So what we're doing here, we're not doing probability. Instead what we're doing is we're looking for the rating as a function of movie when holding the judge constant. Getting rid of those variations in ratings that have to do with different judges and different moods on different days. Okay, so here it is.
Reject.
We reject the null hypothesis here. Yeah, so this is less than 0.05. We would end up rejecting the null. So with exactly the same data, exactly the same observations, when we had when we didn't have this pairing, we ended up failing to reject the null, right? And when we use the pairing, we end up rejecting the null. So which test should have more power if the pairing is meaningful? The first one should have more power. Okay, so why should the first one have more power? Or do you still agree with me? So what is power? It's the probability of... It's the probability of rejecting the null when it's false, when the null is false, right? So here we see a smaller p-value. Are we more likely to reject the null with the smaller p-value? Yes. So we are more likely to actually reject the null hypothesis in this situation. So this is a bit more powerful. When we can account for the differences in individual raters or individual things, right, by pulling out variance, which we did something like that here. It's a bit different because we're ranking things. Basically what we're doing is we're getting rid of error, or we're accounting for error. So we have statistically significant differences in ratings when we control for judge. Okay, so how did we get 10? So here we have Q. Not so sure why it's Q. I'm not so sure actually that the formula that I'm providing is called Q. I started writing this formula, I formulated it differently, and then as I said at the beginning of class, I realized that there was a relationship between this formula and the previous one. So I ended up rewriting the formula, which is mathematically equivalent to what Q was. But it's very similar to what we had before. So what do we see here? How is this similar? How is it different?
Just different, we add the energies, the populations.
Also we use K.
And K, yes.
So this is different.
And the first,
This is different.
but the others is the same.
The other thing is the same. Everything else is the same. What did we have before?
N minus 1.
And 1.
That n minus 1, right? Where here we don't have n minus 1, we have ng. What do you think ng is? The sample size per each group times k minus 1.
Level, K is level.
K would be levels, okay, of what?
Factor.
Levels of the factor, and what's the factor here?
Movie.
Movie, right. Yeah, we have movie, factor movie. And we have 3 levels. So this is like the degrees of freedom for our movie.
Total.
And basically everything else is the same. So the only thing different between this and the previous is just this weight, right? This is just a weight. When you multiply something by something else, you're just weighting it different. So we are weighting this, actually, the weight here is smaller than it was before, right? Previously we had big N minus 1, which was 14. What is this?
It is
5
multiplied with 2.
times 3 minus 1, 10. Yeah. Okay. So, let's work through the example. So here we have the ratings, right? When we did the ratings for each individual judge, right? Aisha said 231, Williams said 231. All of the judges said the first one was 2, the next one was 3, the next one is 1. Now we need to find means, right? So we need to find the means for Old Yeller. So what's that? 2, 3, 1? So the means for Old Yeller is 2, 3, 1?
2.
It's 2, right? 2 plus 2 plus 2 plus 2 plus 2 divided by 5. We've got 2. How about the mean for Forrest Gump? How about the mean for Gomul Yarısı? 1. How about the total? 2, right? 2 plus 3 plus 1 divided by 3, 2. Okay, sweet. So we need to find the difference between each rating and the mean rating, right? So we need to do that, and then we need to square it. So what are our square differences going to be?
Zeros.
Zeros for the first,
1.
1s for our next bunch,
Minus. Again.
again 1, because we're squaring the differences. That's exactly right. Okay, so here we have our squares, here we have our means. Now all we need to do is
Put that.
plug them in, right? So we have the 10. This is exactly what we figured out earlier, which was just 5 times 3 minus 1. So that's that. Now we've got this part is equal to this, and the bottom here is equal to that. Let's verify this. So the top part, is that really 5 times 2, 10? Is that really 10? So let's see, in G, this is going to be 5, right? So now we want to get the difference between each group mean and the grand mean, right? So we have 0 minus, or wait, actually, you guys are working too fast for me. So 2 minus 2 squared, that's 0 squared, right? And then we have
3 minus
3 minus 2 squared, so that's 1 squared. And then
2.
1 minus 2 squared, and that also is
1.
negative 1 squared, but it would just be 1, right? So we have 0 plus 1 plus 1, so that's 2 times 5. That's right, so 10 on top. And then the bottom. So this is just the sum of all of these squares. right? 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that turns out to be correct too. So we have 10 times 10 divided by 10 equals 10. You guys remember what we had for the chi-square previously? Yeah, 10?
That's
Yes, it was
I didn't point it out, so I'm not sure. It is 10. It works. That's it. So why do you think we use the chi-square distribution here?
Sum of squares.
We have sum of squares, right? But previously, when we had a sum of squares and we divided, or we had a mean squares, which is just a weighted squares, divided by another mean squares, we ended up using an f. So why do you think we use a chi-square here instead of an f?
x squared. X squared. F is the relationship between two x squares.
F, it's not the relationship between two, it is a ratio between two sum squares, but it's not the same relationship that we have here. So with the F, it was the relationship of like the effect related to the error.
Now,
Whereas here we have the effect as it's related to the total. Which when you divide the effect by the total, it gives you the percent, right? A percent of chi-square, right? Which then you multiply by some weight, and then you end up back with a weighted chi-square. So this, even though it looks similar to the F distribution, we're actually going to use the chi-square distribution to estimate this.
when we look at the p-value for without ANOVA, without model, and can we use QF
You use QF.
for
So to get the quantile for the F distribution,
and for p-value to find
you should use, if you want to find the quantile, you should use Q chi-square, or Q chi-square, right? Or P chi-square, or R chi-square. If you want to generate data from a chi-square distribution. All right, on Wednesday we will have a review. I plan on doing the review the same way we did last time, so I plan on trying to do one example of each type of question that I'll ask you to do on the test in R, and then we'll go through that in class. So hopefully that should be helpful. If you have questions, come to my office hours.